Okay, so we start with the importing the files and then importing the dataset from the Kaggle Hub um, path, like from their website, and then turning it into a data frame. So we have 5,110 rows and 12 columns, and then here we can see that BMI has some missing values, and then some columns require data manipulation. So I checked the unique values of smoking status so that it can help me with the visualization, and here I saw that there's a high percentage in the unknown smoking status, which is like something bad in the data frame. You usually seek like a full data frame that includes people, like without some unknown or null values. We can also see that there are a lot of never smoked people compared to smoked. Okay, now that I think about it, maybe adding these two is almost close to these, so maybe if we combine them it would be better, but in this case we were not asked to go that deep into the dataset. Here I saw the distribution of people who had stroke or not compared to their smoking status, and I found out that the ratios are not that different. I was expecting to see formerly smoked and smoked much more in the people who had stroke than here. So yeah, so there's no correlation. I also in the beginning I assumed that hypertension, heart disease, and smoking status are the biggest indicators for stroke. So this removes the first assumption regarding the smoking status. Here I checked the heart disease, and we can see that there is some biases because this value is much less than this value. Again, here the ratios are similar, so we confirm that our assumptions are wrong. We start here with with filling the null values. So I filled the BMI missing values with the mean, and then checked if there is null values, and it was 0. Here again all rows are filled. So we start with the columns with the type object. So here I checked the unique values for each object column, and then I started manipulating the data to numbers so that the model can be, so that like it can help train the model. I checked if there is any duplicates, and there was none. So I started with the normalization by dividing by the max, and I figured that the ID column is not necessary for the model, as it would not help with the final result of finding whether there is a stroke or not. And lastly, to fully confirm my assumptions, I plotted a correlation matrix to see if there is correlations between stroke and the assumed parameters. But as we can see, the highest correlation was with age, so my assumptions were wrong. We start with model building. So I identified y to be the last column and x to be the rest of the columns, all except the last one. I split the data with 80% training data and 20% test. Here we started with the sequential way of creating the neural network model. I started by doing one input layer and then one hidden layer with 25 neurons, and then the output layer is 2 because it's either you have a stroke or you don't. I compiled using Adam as the optimizer. Loss function was the sparse categorical corentropy, and the metric is accuracy. Here I created the data, fitted it with the training model with 10 epochs, which means that it would like refeed them for 10 times. The batch size is 256, and here we got 0.95 accuracy. In the beginning it shows that the accuracy is great, but when you start using the 4 metrics, you can see that precision is 0, recall is 0, F1 is 0. So the reason behind this is it is not capturing the positive stroke results. Or yeah, like it's identifying one type and not the other. Here I made sure that this is the case. So we move into the model improvement. Sorry, I'm sick. Okay. Anyways, so the first model improvement method is applying weights for the classes. Because, so as we saw in the beginning, in the data visualization, we saw that people who were identified with stroke is much less than people who did not. So I did some custom weights where 0 is people who didn't have a stroke, and the weight remained the same as 1, but because it was almost 5% of people who had stroke, so I multiplied the weight by 20, because 5 times 20 is 100%, which is which is close to the other class. We created the model, fitted the model and added the class weight, and did the prediction where we had the results as 0.73, or like 73% for accuracy, 16% for precision, 80% for recall, and 26 for F1 score. While the accuracy was lower than the previous model, we overall didn't have zeros in the other parameters, or metrics. So we would say that this identifies the model better. The second strategy was to use a wider and deeper neural network with more epochs. So I added 2 more layers in the hidden layers and made them wider. So I think in the beginning it was 256, if I'm not mistaken. Yeah, it was 256. I added 2 other layers before that, the 1024, 512, and then again it's the same one, but it achieved after running, it achieved similar accuracies to the first time. So this did not solve the problem of identifying the positive stroke results. So if we combine the 2 strategies, so I thought maybe like if I combine both the weight and making the neural network wider and deeper, it would help. But after doing so, you can see here the class weight and the model from previously. So yeah, it achieved slightly better results than the first time I did the weighted the weights, but it wasn't that big of a difference. So I can confirm that making it wider and deeper did not help. So the third strategy was to oversample the minority class. I did a research about, I researched SMOT for oversampling, and I thought it was the best way to use oversampling in this case. So I did the oversampling, did another training dataset with the balanced samples, and then after doing the predictions I achieved an accuracy of 78%, precision of 16, recall of 64, and F1 score of 26%. So after comparing them with the previous strategies, this had the best results. So I decided to move forward with this strategy. Here I'll go back to this cell. Let's move forward and then I'll come back. So here what I did is I added the optimizer parameter because I was using the grid search, and I added the optimizer. So we tried different optimizers here, the Adam optimizer and the RMS prop. So again, here we used SMOT for the oversampling. We fitted the samples. We used the Keras classifier for the model, and then I did define the grid, and then I did the grid search, fitted the results, and here we can see that the best F1 score was 0.86, where the best parameters was the batch size 128, the epochs 20, and optimizer is Adam. So the reason, again, going back to this, the reason I uninstalled scikit-learn, here I installed Keras for the Keras classifier, and I uninstalled scikit-learn and reinstalled an older version, is because there was some problems connecting the Keras wrapper with the scikit-learn, because the new update had some it was different with the parameters and stuff. So yeah, that's why I used the older model. And here I printed the 4 metrics, and you can see that the accuracy here was the best accuracy with 81%, precision of 16%, recall 53, and F1 score 25%. So yeah, for the final answer, while yes, the grid search achieved the highest accuracy, but it took so much time processing, and it was much more complex. As you can see here, it took 6 minutes to process this code cell. So if we're looking for, so comparing this result with the oversampling result, the difference isn't that big. So yes, we can move forward with just oversampling, but because we are we're using it in the healthcare environment, so it's important to try to achieve the highest accuracy and overall metrics, as it would be critical and could help save lives. And as a recommendation, I recommend the healthcare team to not fully depend on the model or any other machine learning model or neural network model, but they can use it as reference, as it does not give 100% accuracy, and sometimes problems are critical, and like one mistake uh, could cause in a death or something.